Okay, we're back in business. All right, so we have several problems with our regression. All our results are nonsense. You all failed the previous homework. I'm sorry, okay? No, it's not your fault. So the point of the previous homework was to lull you into a sense of complacency, like, yeah, we're doing regression now. And that in class, I want to shock you and say, no, you're doing it all wrong. All right, and what's going wrong is going to take us a couple of weeks, so we're gonna figure this out slowly. All right, we're gonna get most problems solved to some degree today, but we'll see other solutions in the coming weeks as well. All right. um by the way, Gil, can you remember that our batteries are in here, okay? We don't leave them here, okay? All right, let's move on. So we got several problems we identified. One is nonlinearity. Let's start with that one. Okay, our data is not linear, so what do these slopes even mean? All right. Okay, let's take a look. So let's look at some linear relationships in our data. And there are not too many perfectly linear relationships, but some are better than others. Okay. For example, um, in this example here, I'm just regressing miles per gallon over the model year. And remember, the model year was like 70, 71, 72, 73. Like it was just the year of the car was made. Okay. So from 70 to about 1982. And you'll notice that, of course, cars don't have 70.1 and 71. So um, the variables are somewhat kind of ordinal, but you can think of them roughly in a continuous sense as there's like, 12 different levels here. So from 70 to 82, the regression line we draw goes more or less through the middle of this plot, right? Yes? Model year on the x-axis, miles per gallon on the y-axis. Now you'll notice for some years, okay, it doesn't quite go to the middle of the 71 range, right? The range of miles per gallon in 1971, the regression line kind of goes to the bottom of it, not to the middle of it. For some years, like, I don't know, 1974, it runs roughly through the middle of it. So on and so forth. But overall, the regression line kind of runs to the middle of it because the relationship is roughly linear. Are you with me? Yes? Okay. Um, and I've drawn line segments, but you can barely see them, these red line segments. From each point to the regression line, these are the residuals. All right? They don't look very spectacular because, again, on average, these are running roughly through the middle of each year's points. All right? If I ran this regression through uh, actually, I think there's something wrong in the slides here. This should not be horsepower. This should be model year, I think. Um, so what we'll generally find, and let me actually run it. Do I have it here? Let me go find the nonlinearity section, and let me actually try to run this. All right. No regression analysis. Where are you? Where are you? What am I looking for? Okay. No, that's not what I'm looking for. Um, okay, anyway. I believe this plot, I think this is wrong. It's not HP, this should be just regression, REGR, okay? So, or your regression. I've got this all confused, but ignore the code for a moment. Just look at the visualizations, okay? TAs, please tell me the slide number 11. I need to fix the code, all right? So by and large, if I do this regression and I plot the residuals, I should see something like this. It's not like perfectly normal, but it is kind of sort of symmetric, okay? The residuals are sometimes negative, sometimes positive, right? For some of these points, have a negative residual, some of them have a positive residual, okay? Residual being the distance from the actual y points to the regression line, straight down or straight up, okay? So some are negative, some are positive, but they're more or less symmetrically distributed around zero, the residuals, okay? Moreover, if I was to plot on the x-axis the model year and on the y-axis the residual, I get a fairly interesting plot. It's basically this plot with the regression line being flat in the middle, right? It's essentially the same plot with the regression line being this flat line at 0. And by looking at the residuals, I'm just looking at how far is each point from the regression line. So it's really this plot with the regression line being drawn as a horizontal line at 0, and each distance to the points being the distance being the distance from the regression line. Okay, and as you can see, so the y-axis is the residuals here. Some points their residual is positive, some the points the residuals are negative, but overall half the residuals lie on the positive side, half lie on the negative side. And there's no pattern to them. They're kind of randomly on the positive or the negative sides. Okay? That's for a fairly linear relationship. Let's look at a fairly non-linear relationship, like miles per gallon to horsepower. Here, we've got horsepower on the x-axis and miles per gallon on the y-axis, okay? We have a roughly banana shape, as we talked about before. Okay, roughly banana shape, or plantain, depending on what you're eating. Okay, all right. And you'll notice something interesting here. On the left-hand side, most of the points have positive residuals. Most of these points are above the regression line. There's a few points below the regression line, but there's a big cluster of points that are above the regression line. Do you see that? Right? As we get to the middle, there's very few points above the regression line. Most points are actually below the regression line. And as we get to the right-hand side, right-hand edge, there's no points below the regression line. All the points are above the regression line. This is what nonlinearity looks like, right? This straight regression line doesn't really capture this relationship. Agreed? Right? The code for this visualization is on the right-hand side. I won't really get into it, okay? What does this mean if we looked at the residuals? If we looked at the residuals, you can see the residuals are somewhat symmetric, but a little bit skewed, right? It kind of like tapers off to the edge here. And if we do this plot, where horsepower is the x-axis and the residuals are the y-axis, it's again kind of similar to this plot up here, but we've kind of straightened this regression line out and drawn it as a flat line, and just showing you the distance of each point to the regression line. You can clearly see this weird like banana shape here, right? And this is really screwing up our results in interesting ways, all right? It means that we can't really talk about a standard error of coefficients. The residuals aren't even like distributed normally at all points. And this right edge is most problematic. The residuals are all in one direction, which completely violates the assumptions of regression that the residuals should be normally distributed with a mean of 0 across all values of x. Here clearly, as x changes, the residuals change in pattern. They go from being largely above the regression line to being largely below the regression line to being almost entirely above the regression line again. All right. Our slope is kind of meaningless because it doesn't really capture a non-linear relationship. And standard errors, t-values are all kind of undependable here. Okay. So what can we do here? There are non-linear ways of doing something like regression, okay? But I won't go into that right now. An alternative is we can transform our data so that it appears to be more linear, all right? We can take this banana and we can like just straighten it out a little bit, okay? Now that might worry you a little bit, like, how are we going to interpret those coefficients if the data is not the original data? Like it's not horsepower anymore. It's like a flattened version of horsepower. Like our interpretation is going to get screwed up. As I'll show you, there's some transformations we can do which have very nice interpretations, in fact. All right, so let's take a look at one very popular transformation of data, which gives us surprisingly interpretable coefficients, interpretable slopes. All right. The transformation in particular that I want to look at, all right, is log transformations. So let me first show you what a log transformation does to our data. Then we'll come back to what does log actually mean and what does it do. All right. So here's a histogram of horsepower, just the horsepower data, not horsepower versus miles per gallon, just horsepower. Histogram of horsepower shows you the distribution of horsepower. All right. As you can see, our horsepower variable itself is not very normally distributed. It's highly skewed to the right. All right. A lot of our data is here, and then a long tail develops over here. Let me take the log of horsepower. Okay. So I'm taking the horsepower data and conducting this log function on it. Many of you might have forgotten what log does. I'll cover it in a moment, but let me just show you the pleasing result it has. When I show you a histogram of the log of horsepower, take a look. Ooh, it's become a lot more normally distributed, right? Like it's become more symmetrically distributed. This was our original distribution, and now this is our log transform distribution. All right. What does it do for the regression overall? What does log even mean? All right. So the next slide kind of gets into what does log do. We're going to throw away all the data, create some synthetic data, and see what does log do on just some artificial data. All right. So let's start by creating some artificial x values. Okay. So x is just a sequence of 1 to 100. Okay. These are some artificial x values, no actual data. And I'm going to create a non-normal y value. So y's are going to be the value 1.05 raised to the power negative x. So this is an exponential relationship between x's and y's, okay? And let's plot what it looks like. It looks like this, all right? X-axis, y on the y-axis, all right? We have our perfect banana shape, all right? This is not the perfect banana, but the middle of the spine of the banana, if you will, okay? So this is a non-linear relationship. It's an exponential relationship, okay? And if I was to draw a regression line of just y regressed over x, we get a pretty ridiculous regression. This is obviously not coming close to estimating this relationship. A very poor. And in fact, it reminds me a lot of our regression of horsepower, right? Miles per gallon over horsepower, because as you can see, on the left-hand side, all values are above the regression line. In the middle, values are below the regression line. To the right, values are above the regression line. All right? So this is kind of creating a similar nonlinear relationship to what we saw over here. Just a very perfect version of that nonlinear relationship. Okay? Okay. Um, okay. And if we look at the residuals of this regression, our residuals again have this skewed distribution. I'm just taking the regression of y over regress over x, looking at the residuals and plotting the density function of it. Okay. So this again kind of begins to look a little bit like this residuals we saw for our horsepower regression, right? Doesn't this kind of look like that? Kind of. And if I do this plot of X versus the residuals, we get a shape that is very reminiscent of this picture we saw before, right? Isn't that kind of like that picture? Just a very perfect version of that picture. Okay. So what could we do to transform these variables to make them look a little bit nicer? Okay. Here is a quick definition of what log does. All right. Excuse me. Log. All right. So the definition of log is kind of here. And here, as you can see, I'm plotting the values 1 through 100 versus log of 1 through 100, just to show you what log does. Log gives you the shape like this, where the values of log increase, but kind of sort of asymptotically, like how fast the increase decreases, the rate of increase decreases, if you will. Okay. And um, taking the log of just like a value gives us something like this. However, if we take the log of a value that is of certain data that is raised to a power like x, this is maybe from a long time ago in some math class you had, this expression resolves into this expression where if so remember like we had this y expression, which is some constant 1.05 raised to the value x. If we take an expression like that, where b is 1.05 raised to the power x, if we take the log of that, that actually is the same as taking the log of this constant times x. And let me show you what that looks like. Okay, so this time, instead of plotting, so earlier I plotted x versus y and drew the regression line. This time I'm going to plot x versus the log of y. Bang! It's a straight line. X on the y-axis, log of y on the y-axis. Now the relationship is perfectly linear. So log can often take a slightly nonlinear relationship and straighten it out to a linear relationship. Why is it? Why does it work this way? Because if you took a linear variable and logged it, it makes it nonlinear. So if you take a nonlinear relationship and you do the log on it, it can make a nonlinear. It can bend it the other way into a linear relationship. All right. And actually, if I draw the regression line here, it's a little too perfect. The regression line runs perfectly through x and log y. It's too perfect. All right. Okay. We can use this idea to take logs of variables in regressions. And let me show you several ways we can do it. All right. We could take the log of x and then regress y over the log of x. Okay. I showed you the log of y before, but you could also take the log of x. I'll show it to you in every combination. Bear with me. Okay. So for example, here, I do miles per gallon over the log of horsepower instead of horsepower by itself. All right. You might notice that the relationship has improved a little bit. It is not so banana shaped as before. It's improved a little bit. At the very, very right edge, we do have problems with some points still being completely over the regression line, not under it as well. On the left-hand side, okay, they're a little bit over, a little bit under. The middle is a little bit better than we had before. Okay. Now, does taking the log of horsepower ruin our explanation? Because how do you explain to somebody, yeah, here's the regression coefficient, It's the log of horsepower. People are going to be like, what? That makes no sense. However, taking the log actually has a really interesting interpretation in regression. The generic explanation is this: when you regress y over the log of x, it means that the coefficient has the following meaning. A 1% change in x leads to whatever beta is, whatever your standardized regression slope is, divided by 100 units of change in y. All right? So here, when I do miles per gallon over a log of regressive a log of horsepower, the coefficient, the coefficient is this one, okay? And the way you interpret this coefficient, minus 18, is that a 1% change in horsepower leads to this divided by 100, 0.18 decrease, because it's negative, in miles per gallon. This is actually kind of interpretable to people, all right? A 1% change in horsepower leads to this much drop in miles per gallon, all right? So log has this interesting property that in a regression, you can interpret it as a percent change, all right? And generally, human beings are quite okay dealing with percent change. So they say, oh, so if I change my horsepower by 1%, this is the change. So what if I change it by 50% or by 100%? People can deal with percents. They're okay with percents. Okay. And by the way, when I do that, this is what the distribution of the residuals looks like. It's not quite normal, but it is a far more symmetric than before. Okay. This picture is much more symmetric than this picture. Here we had an obvious skew before. We have a little bit less of a skew in this picture, okay? However, this picture, where we look at just horsepower versus the residual of horsepower, not so pleasing yet. There's another way we can apply log, which is I could take the log not of the x, but of the y value. Let's look at that here, okay? So I'm taking the log of miles per gallon and I'm regressing it over just horsepower. It has a slight but maybe negligible improvement over our original data. A slight but maybe negligible improvement. Maybe a slight. Okay. The residuals look quite nice, actually. This looks like a nearly normal distribution. This plot is still not entirely pleasing, but it's getting there. Okay. Well, does taking the log of the dependent variable have a pleasing meaning? It actually does. If you take the log of the y, then it means that a 1 unit change in x leads to 100 times the coefficient change in y. So if we take the log of miles per gallon and regress that over horsepower, so we're taking the log of the dependent variable now, we get a coefficient of minus 0.007. In this case, because the dependent variable is taking the log, we multiply this coefficient by 100. And the interpretation now is that one more horsepower, not 1%, one more horsepower leads to a 0.73% decrease in miles per gallon. Okay, almost 1%, but a little bit less than 1%. So log has this nice property that one side of the explanation becomes a percent, the other side stays what it was before. All right. Are you okay with this? So log is one way of improving the nonlinearity. And sometimes it has a tremendous effect and it really straightens out your data. Sometimes it does a little bit, but not a whole lot. There's one more trick up our sleeve with log. If I can take a log of the dependent variable or I could take a log of the independent variable. Then there's a third combination, take a log of both. I could take a log of both sides of this regression. I could take a log of y and also take a log of x. Okay? And look at my regression here. Isn't that plot look nearly linear now? This is a lot better. Listen, I don't know which one works when. You can try all of them out on different, whenever you have nonlinearity, you can try each one out. As long as the nonlinearity is basically your data bending one way or the other, a little banana shape, logging the y or logging the x or maybe logging both, try these out to see which one gives you the most pleasing results. Okay? And as you can see here, we have a nearly linear relationship once I've taken the log of both. That's nice. And if you look at the residuals, it's a nearly normal centered around 0. And this plot too, in this plot, this is a plot of the x variable, which is once again horsepower, versus the residuals of horsepower, the residuals of the regression. This begins to look a lot like the example of when we had a linear relationship. We were looking at model year. And remember this plots? Where at every level of x, the residuals seem to be distributed symmetrically on both sides. And as x goes up or down, like the distribution doesn't seem to change. So similarly here, excuse me, okay? Similarly here, yes, there's some clustering here, but by and large, as x increases or decreases, the distribution of the residuals seems to be symmetrically distributed to either side of the regression line, to the either side of 0. Okay? So in our case, this final solution gives us the most linear relationship. The residuals match the assumptions of regression of being fairly normally distributed symmetrically on both sides of the regression line. And as x increases, the variance of the residuals does not seem to change too much. Okay? Meaning, if x is 4, let's say 4.5, the residuals are from roughly minus 0.4 to roughly positive 0.4. And when I look at an x value of about 5 or 5.25, like around here, once again, the residuals are from roughly minus 0.4 to positive 0.4. Okay? The distribution of the residuals does not change depending on the value of x I'm looking at. These are the classic assumptions of a regression that we want. However, does taking the log of both sides give a pleasing meaning? It actually gives a very pleasing meaning. When you take the log of both sides, then a 1% change in x leads to coefficient percent change in y. Very simple. So in our case, when we did this regression, log miles per gallon over log horsepower, the coefficient was minus 0.84. This tells us that a 1% change in horsepower leads to a 0.84% drop in miles per gallon. It's percent on both sides now. All right. There are other types of transformations, but I just want to show you log transformation because it often does the trick and it has a very pleasing interpretation. It just means that one side or both are interpreted as percent change rather than one unit change. Okay? Any questions on this? Are you okay with this? So this is one way to combat nonlinearity, is transforming your data. And I've showed you one type of transformation. It's log transformation. There are other types of transformations that I won't get into. However, I would like, if anybody would like to do it, I'd be very happy. Go Google around. You might find a nice resource that explains different types of transformations and when to use them. Okay? Yeah.
So, how do we know the performance of the transformation of
Oh, um, the way to do it is to actually look at the residual plots. Look at the plot of the residuals, and then for each x variable, look if the residuals, if the pattern of residuals stays the same throughout all values of x. If you can meet those assumptions, then you're good to go. But if you still have problems with like this is still not great. Okay? So how do you do it? Look at the residuals, analyze the residuals. If the residuals are normally distributed symmetrically throughout for all values of x, then you're good to go with your interpretation. All right? So one of the things I wanted to introduce to you today is, apart from log transformation, is residual analysis. Analyze your residuals. This is kind of interesting because residuals, we just call them error. And error sounds like something you throw away. But actually here, the error is actually quite meaningful. Is it not? I think it is, right? There's actually some value to interpreting the error. All right. So that's all I want to say about non-linearity. Okay. Let's just stretch out. We're done with non-linearity. Woo! Let's look at another problem that we had in our data sets. Okay. So I'm assuming with log transformations, or maybe another transformation, but at least with log doing one side or the other, we can solve most of the nonlinearity problems in our data. Okay. I'm not going to do it for the entire big full regression we saw earlier because that's your homework. Haha. Okay. All right. Let's move to another problem. And the other problem is called multicollinearity. And let's see what this means. All right. If we look at our data, we notice that, and this is, by the way, a correlation table of our data. So nonlinearity done with, let's move to multicollinearity. Okay. So let's look at the correlation of our variables. And I am not interested in the origin because the origin is a categorical variable. It's a little weird to look at the correlation of categorical variables. So origin is our predictor number 8. Okay. And what we not predict is variable number 8. Miles per gallon is number 1, and acceleration is number 6. Origin is number 8. So what I'm going to do is I'm going to remove the 8th. I'm going to look at all except the 8th column. You can do it like this. Cars, and I tell it the columns. -8 means all except the 8th. If I wanted to remove more than one column, I could do like that. Oh, excuse me. I could do it like that. If I want to remove, let's say, 2 columns. But I want to just remove column number 8. And then I'm going to run a correlation. I'll look at the correlations. Okay, let's do that again. A little bit more space. What you'll notice here is that some of our explanatory variables, like weight, is heavily correlated with certain others. Like weight is heavily correlated with cylinders. Huh, why is that? By the way, I assume weight is weight of the engine. I'm not sure if it's weight of, or maybe it might be weight of the car. Let's say it's weight of the car even. Why would the weight of the car be correlated with the number of cylinders in the engine? The cylinders are heavy, the cylinders and pistons are heavy. That's one possible explanation, that I need more metal to make those extra cylinders, to making the car heavier. Any other explanation? You need more fuel. I'm guessing these are dry weights. These are weights without the fuel gas in the tank. My guess, okay? Ta-da! This is probably a better explanation. When you have a bigger car, you probably need a more powerful engine, okay? So you can't really look at the weights and the number of cylinders independently because bigger cars have bigger engines, right? Like if I'm driving a huge truck versus a small little grocery getter car, right? I'm gonna have a completely different size engines, all right? And this is problematic because that's also true for displacement, because displacement is, the volume of those cylinders combined. Bigger cars are gonna have, more displacement. They're gonna need more power to move that car. Horsepower, similarly, you need a more powerful engine if you got a bigger car. So one of the problems in our regression analysis is many of these variables have almost the same meaning. For example, cylinders, displacement, and horsepower are all telling you roughly how strong is this engine. Putting three different variables that have the same meaning into a regression, it's not going to give you like something very useful, all right? Because you're asking for the same explanation again and again and again. And regression can't do that. It just cannot do that, all right? And we'll see what happens when we try to do this, all right? So what happens when many of our independent variables are highly correlated with each other? Let's see what happens. I'm going to start with a simple regression. And here, I'm just regressing miles per gallon over displacement. Note the coefficient is about minus 0.8. Notice the standard error is about 0.029 or 0.03. Okay? Now, I'm going to add one more variable to this regression. And the variable I'm going to add is something that displacement is highly correlated with. I'm going to add the weight. So now I've got displacement and weight. And they're highly correlated, so they're basically saying the same thing, almost. They're almost saying the same thing. There might be a slight difference in what they mean, but it's relative. You've got a heavy car with a powerful engine. Heavier cars always have more powerful engines. So it's hard to distinguish these two explanations. All right. Let's see what happens when I run this regression and take the summary of it. The results are here on your handout to see. Look at the coefficient for displacement. It went from a very healthy value of minus 0.8 and it's now dropped to about minus 0.2. The coefficient has dropped by a fourth to a fourth of its original value, right? Look at the standard error. The dispersion, like how far could this estimate vary? Well, the standard deviation of its, how much its dispersion would be was 0.029. It's now gotten inflated. It's about 0.07. The standard error is like 3 times bigger now. Our estimate of this coefficient is now much wider. Like sometimes it'll be very small, sometimes it'll be very big. We've inflated the distribution of this estimate. And unsurprisingly, its p-value went from, what the hell is that? That's almost perfectly zero. Is 0.00016 times, and now it's just 0.004, 0.00005. It's becoming harder and harder to argue that this coefficient isn't just zero. All right. Why did this change? So let me give a kind of a casual story of what's going on before we look at the numbers again. Essentially, what's going on is that weight and displacement have the same meaning. We cannot really tease them apart. Okay? For example, let me just do a silly demonstration. I won't do a demonstration so I don't embarrass anybody. But let's do a thought experiments, okay? Let's say that I have one of my TAs standing by the light switches, by the switches. Well, I don't know if they're light switches, but they're standing over there by the switches by the wall, okay? And I tell you this, and I tell all of you the story that every time that the lights in this room, I can change them by clapping my hands. You know, like you can buy that, right? Clap on, clap off. You can clap and then the lights go on, clap, the lights go off. You can buy that sensor. So let's say I tell you that I've changed the lights in the room so that every time I clap, they turn on. And if I clap 3 times, they turn off. And let's say that every time I clap, it really does turn off. And if I clap 3 times, it really does turn back on. Would you believe me? Probably you'd believe me. But then, out of the corner of your eye, you notice that one of my TAs is standing by the switch. And every time I clap, he turns the switch off. And every time I clap 3 times, he turns it back on. And you say, wait a minute. Why are the lights going on and off? Is it because I'm clapping? Or is it because of the switches? Which is the better explanation? Switches? But what if the lights are really, clap activated and I don't know what the hell my TA is doing over there? But for whatever reason, I don't know, maybe let's say it's Metab, he's standing over there and playing with the switches and it just happens to perfectly correlate with what I'm clapping. It becomes very hard for me to convince you which one is correct. And it becomes very hard for you to disprove that it's my clapping that's turning the switches on or off, right? Because the two, the TA playing with the switches and my clapping, correlate perfectly. This is a problem with reality, not a problem with regression. You cannot really distinguish which explanation it is, all right? And that's the same thing we're happening with displacement and weight. As displacement goes up, weight goes up. Displacement goes down, weight goes down. Which one should regression credit for the change in miles per gallon? It doesn't know. So what does it do? We'll talk about mediation in another week. We'll talk about mediation in another week, okay? Just play with this idea for now of collinearity. You've got two explanations which are almost identical. By themselves, the displacement explanation was very strong explanation, minus 0.8 estimate. I added weight, and displacement is now not such an important explanation anymore. Because what's happening is regression is taking these explanations, and since they're almost identical, it's just splitting the explanation between the two of them. Okay? It's splitting the explanation between the two of them. Which one gets more credit? The one that is a little bit more heavily correlated with miles per gallon. Okay? And weight happens to be slightly more correlated with, I think, with miles per gallon. What is the correlation between miles per gallon and, oh, it's in the very faint letters up here, and weight is about minus 0.83. And the correlation with displacement is 0.8. It's a little bit less, minus 0.8. All right? So since weight has entered the picture, they have very similar correlations with miles per gallon. So regression is just splitting the explanation between the two of them. All right? And as a result, the coefficients are kind of meaningless because this coefficient, which should explain how much miles per gallon changes, it's the credit is split between these two variables because they both have similar correlations with miles per gallon, and more disturbingly, they have very similar correlations with each other. Me clapping, the TA playing with the switches. All right. So these coefficients they're not interpretable. Regression is just splitting it one way or the other. Okay. A typical symptom of multicollinearity is when you add a new independent variable to the regression and the coefficients of other variables change. If you're adding variables to your regression and coefficients are changing, that's a symptom of multicollinearity. Regression is saying, oh, I suddenly have a new variable that has a similar explanation as another variable. I better split the credit between them. Okay. And the other symptom is your standard errors change. As you saw here, the standard error got inflated about 3 times. It went from about 0.03 to about 0.07, right? More than 3 times inflated. So these are the symptoms of multicollinearity. If weight was not at all correlated with displacement, the coefficient of displacement would not have changed. Its standard error would not have changed. Okay? And that is why in a regression, we call the x variables independent variables. They should be independent of one another. They shouldn't be so highly related to one another. Okay? So another problem with that big regression you ran for your homework is that several of these variables are highly correlated with each other. Weight, displacement, cylinders, horsepower. These are all highly correlated with each other. Their coefficients are kind of meaningless because regression is just splitting the effect between them somehow. So you cannot really tell how much each one has an effect on miles per gallon because they all move at the same rate. Okay? And this is a big problem. And moreover, their standard errors are all terribly inflated. You probably saw when you ran the full regression, back up here, sorry to make you dizzy. You probably saw when you ran the full regression that weight had a very strong correlation. The coefficient of weight had a very strong correlation. However, horsepower had an insignificant correlation. Cylinders had an insignificant correlation. But actually, they should not have insignificant correlations because they all have roughly the same meaning. The problem is that weight is getting almost all the credit and the others are not getting enough credit. And their standard errors are all inflated, which means it's hard to detect significant differences. All right? This is a symptom of multicollinearity. If you just ran the full regression, you wouldn't know that. But as you put just one predictor and you start adding more predictors, you start noticing this kind of thing. You're like, hey, displacement was significant. It's suddenly less significant now. Or cylinders was significant. When I add weight, it's insignificant. The standard errors have completely changed. What's going on? Multicollinearity. All right? So regression really, for explanatory purposes, it really works best when your x values are not highly correlated with each other. All right? Interestingly, and you may, if you take a data mining class elsewhere, you learn that it doesn't actually affect your prediction of y, but the coefficients and standard errors are all completely wrong. The predictions still work out correctly, all right? Meaning your predicted values or perhaps even your fitted values don't change a whole lot, but your coefficients and standard errors change completely, all right? You'll find that out a little bit in your homework. Okay, so multicollinearity is definitely a problem in our data set. Sorry, I'm going to scroll down. Hopefully, the last time I'll scroll down like this, okay? Up and down, right? Changes in coefficient, inflation of standard error, symptoms of multicollinearity. Well, what can we do? I don't know what to do yet. Maybe you'll find out in your homework, or maybe in the coming weeks we'll talk about what to do here. Because this is a reality problem. This is not a statistical problem. Like I said, my TA playing with the switch and me clapping. There's nothing you can do unless you could unless you could grab my TA and move him away from the switches. There's not much you can do, right? You cannot just look at the data and then figure it out. The data is not going to help you. Okay, so we have to do something else. Let's focus on one aspect of multicollinearity, and then maybe for your homework, we'll try to see one solution. In later weeks, we'll see some other solutions to multicollinearity. Okay? So remember, I said that when we add correlated x variables, that the standard error gets inflated, right? I said that at least 5, 6 times now. The standard error is really the standard deviation of this estimate. Okay? If you take the square of the standard error, you're going to get the variance of this estimate. All right. So if you take the standard, if you take the standard error and you square it, you're going to get the variance of the estimates. Now, either way, standard deviation of the estimate, variance of the estimate, we're talking about the dispersion of this estimate. How widely distributed could this estimate be? I don't know how to, I'm not going to try to fix this multicollinearity problem in class, but I am going to give you one way to diagnose the multicollinearity problem, to detect it. Okay? Well, of course, you can look at the correlation tables, but sometimes a high correlation does not have a super bad effect. Sometimes a small correlation has a big effect. It's a little bit tricky. So I'm going to give you a diagnostic tool which helps you detect that you have multicollinearity that is inflating your standard errors. Or actually, in our case, we're going to detect it's inflating the variance of the estimates, the square of the standard error. Okay? How much multicollinearity is inflating the standard errors or the variance is called the variance inflation factor. Here, factor means like a multiplication, like how many times is the standard error inflated by, all right? So, and we use this tool to detect multicollinearity. And it may be a little bit unusual, so please try to follow along and we can ask questions, all right? So this is the way we're going to do it. So let's say we have this regression of miles per gallon regressed over cylinders, displacement, horsepower, weight, acceleration, model year, and origin. That's pretty much everything. All right. We want to know, is cylinders, is its standard error and coefficient being affected by multicollinearity? All right. And this is the way that you can, and here's the way that you can detect that, yes, the cylinder's coefficient is probably off, its standard error is highly inflated. This is how you detect it. We use a metric called the variance inflation factor, and this tells us by how much the variance of this estimate is inflated. And the way we calculate it is with this formula here, but it's not exactly what you think it is, so take a look. It's 1 minus r squared, but this is not the r squared of your regression. This is not the r squared of y, okay? It's a different r squared, and here's what it is. This r squared is actually the r squared you would get if you regressed this independent variable, like cylinders, over all the other independent variables. So if you were to regress cylinders over all the other explanations, displacement, horsepower, weight, acceleration, etc., etc. If you were to do that regression, so forget miles per gallon, forget the dependent variable. We're going to do a new regression where cylinders is now the dependent variable, and all the other explanations of miles per gallon are the independent variables. We're going to do that regression and get an r squared value. Okay? What is this r squared telling us? This r squared is telling us how well is this cylinders variable explained by the other independent variables. This r squared is a multiple correlation squared. R by itself would tell us what is the correlation of cylinders versus all the other explanatory variables, right? Because remember, big R is a multiple correlation of your dependent variable over and the independent variables. In this regression, the dependent variable is cylinders. So the R squared here is, the R here is how correlated is cylinders to the other explanations like displacement, weight, etc. And R squared is the square of that correlation. And it has another meaning, which is how much of the variance of cylinders is in common with the variance of those other factors, like displacement, weight, horsepower, etc. And we're seeing here that 90%, like Cylinders, 90% of this phenomenon of how many cylinders you have is explainable by these other predictors. All right. What we can do is we can take 1 over 1 minus that r squared of cylinders regressed over the remaining explanations. And that gives us a variance inflation factor. So 1 divided by 1 minus the r squared of the cylinders regression. And that gives us a variance inflation factor of 10. What this tells us is that the variance of this estimate, which is the square of the standard error, the variance of this estimate is 10 times bigger than what it would be due to multicollinearity. All right? And the standard error, if we take the square root of the VIF, the standard error is inflated by about 3 times. So what the VIF tells us is, given a variable like cylinders, how much is the variance of this estimate inflated by? Not the estimate itself, but the dispersion of this estimate. How much is that inflated by due to multicollinearity? And we're seeing here a VIF value of 10, which is extremely high. Okay? Yeah.
Is there any value that you can consider like, okay, this is like acceptable, this is not acceptable?
Thank you, Stephanie. Let's see here. Great segue. Yes. Possibly, let me give you this rule of thumb. And for your homework, I'm going to ask you to figure out why this is my rule of thumb. But my rule of thumb is, if your VIF value is greater than 4 or 5, you have a high variance inflation problem. Why 4 or 5? I'll give you some hints and ask you to try to figure out how I'm coming up with this rule of thumb for your homework. Okay? But generally, if VIF value is bigger than 4 or 5, you can say, yeah, we have a multicollinearity problem here. All right? Yeah.
BIF equal to SST divided by SSE.
Yeah, but for a completely different regression problem. It comes from the R squared. It is an R squared, but it comes from the SSR and SST of this regression of one of your X variables regressed over the other X variables, not the regression of Y over the X variables. Okay?
Of these cylinders, right?
Yes, yes.
So SST.
It is related to that totally because R squared is SSR over SST. So, and 1 minus SSR over SST is SSE over SST, the error variability over the total variability. So 1 over that is basically total variability divided by error variability. It's very much related to it, but for this regression model. Okay? Yes.
Why don't we write like that? SSE.
Because it's for 2 reasons. One is it's very easy to get the R squared value in multiple ways. One is SSR, SST. The other is just a correlation of Y, Y hat. Okay. The second thing is the R square itself tells you something. The R square of this regression of an independent variable over the other independent variables tells you how strongly the cylinder's variable is explained by the other independent variables. So this R squared itself already has an interesting meaning. And by doing 1 over 1 minus, okay, we get this metric. Fine. All right? Yes.
Is there another rule of thumb, sorry, for R squared? For example, like here we say like 0.9 is high enough, right? So that's why we're saying like,
Yeah, remember earlier I said 0.7 is high, and the reason being that at 0.7, half the variance is explained by your independent variables. Here, yes, we could use a rule of thumb here, but by and large, we prefer to use the VIF value. You'll see in your homework why we use the VIF value, or at least I'll ask you to figure it out. Question?
So does the VIF matrix have to do with the model progression, or it is just a diagnostic?
For now, it's just a diagnostic. For your homework, I will suggest a way you could use this to build up your regression model. You'll see for your homework. Okay? I don't want to give it all away in class because then, what's the fun in that? I like it when I like to design homeworks where you're not just doing what I did in class, you're kind of innovating a little bit, using the concepts in class. I know it's painful, but it'll make you stronger. Okay? For now, use it just as a diagnostic. And by the way, this is just a diagnostic that I've showed you for cylinders. You could run a similar diagnostic for displacement, horsepower, weight, acceleration, all of these. You could run similar VIF diagnostics, okay? All right.
But would it be redundant for some of them?
For some of them, yes, but you don't know that until you run it. You don't know that till you run it.
And you never have to take into consideration dependent variable, right?
The dependent variable?
In this case, like,
No, you don't, because what you're really asking is there collinearity between our independent variables? So we can ignore the original dependent variable for a moment and just do these comparisons within the pool of independent variables. Okay? Yeah.
so we'll do this part for the regression analysis or after the regression model.
You can do it before the regression model if you know what your independent variables are. You don't have to regress it. You don't have to regress the dependent variable. You can start with your pool of independent variables and diagnose them all, right? Because
We can see the correlation matrix.
you could also see the correlation matrix. However, as you'll see, the correlation matrix gives you bivariate comparisons. It doesn't give you a holistic impression of one independent variable against all the other independent variables, because the correlation matrix is a simple correlation of two variables. This R squared, this R squared is a multiple correlation, right? So we're getting a holistic idea of how is one independent variable related to the other independent variables. The square root of that R squared is a multiple correlation. So it's the same thing as looking at a correlation table, but it's more powerful because you're looking at multiple correlations now.
So can we know that the cylinders is correlated to our independent variable by looking at a summary of this regression model?
You can know it is by doing this simple regression, no, by doing this regression. Cylinders regressed over the other independent variables.
My question is that how we know the cylinders is truly correlated, collinearity to our independent variable. How do we know that?
Through the VIF analysis. So here's the thing. If you just look at the correlation table, it's possible that cylinders has a medium correlation with another variable. But then it also has that same medium correlation with yet another variable and yet another variable and yet another variable. It's hard, you'll start off looking at all these different columns and rows of the correlation matrix to make a decision. And even then it'll be a subjective decision. Whereas this simple regression here, not simple, but this regression of regressing cylinders over the other independent variables captures all of them at once. And yeah, you have to do it again and again, once for cylinders and once for displacement regressed over cylinders, once for horsepower regressed over cylinders.
Moreover, the rest of this
Yes.
identify, maybe they have multiple
Yeah, so you take them one by one and you say cylinders over everything except miles per gallon. Displacement over everything, including cylinders. So you do them one by one. Okay? And you come up with all your VIF values. Your VIF values is just basically a rescaling of this R squared value. So it's no different than this R squared value. It just gives you an inverse meaning of it. All right? And we'll talk about this R squared and the VIF value, the relationship in more detail next week in class. All right? Just play with this. Just play with this, okay? So essentially, we're trying to detect multicollinearity using a coefficient of multiple correlation, which is really this r squared. Okay. Once again, an interesting interpretation of R and big R squared. Big R is a multiple correlation. So by doing this regression, the big R squared really tells you whether cylinders has a relationship with all the other variables or not. And you don't have to look at a big correlation matrix and, interpret all the different cells, try to figure out, is it too many, too less? What is it? Okay. It gives you a one-shot number to tell you the correlation, a multiple correlation. Okay. Play with it. We'll discuss it again in class next week. All right. Okay. I got 5 minutes left, and I'll show you my last thing I want to show you. We're going to go back for just a brief second to our good friend, the bootstrap. And let me show you how we're going to use it. Intervals. Okay. All right. So remember, so let's take this relationship between horsepower and miles per gallon, but we know it's a nonlinear relationship, so I'm going to do log of both, okay? Log horsepower, log miles per gallon, all right? And I know that there's a regression line, this is a dark line, between log horsepower and log miles per gallon, all right? Let's say I want to know the confidence interval of this coefficient. So here is a summary of the relationship between log horsepower and log miles per gallon. It's minus 0.84, which means a 1% change in horsepower leads to a 0.84% drop in miles per gallon. All right? But what's the confidence interval of this number? Like, is it always going to be 0.84? Could it be as small as 0.5? Could it be as small as 0? Like, if I was to have a different sample, how would this coefficient change? There's two ways to answer this question. One way, and it's in the bottom of your slide here, but I'll show you in more details here. One way to estimate what is the confidence, let's say the 95% confidence interval of this coefficient. How big could it be? How small could it be? If I had different samples of data. One way is to do it parametrically the way we have always learned. We take our estimates, and by the way, I'm going to look into the summary object. Remember the summary object? I'm capturing it here, and I'm going to look at the coefficients, and I'm going to get the coefficient out of it. So estimate is now the coefficient of log horsepower from this summary table. It's this number right here. Okay. Standard error, and again, I can look at the summary object and say for log horsepower, tell me the standard error. That's my standard error, which is really the standard deviation of my coefficient. What is the 95% confidence interval? Pretty simple. It's the estimate plus or minus 1.96 times the standard error. And that tells me that coefficient of log horsepower could be as small as minus 0.89 or as big as minus 0.79. That's the 95% confidence interval of this estimate. Assuming all the other assumptions of regression are correct, residuals, normally distributed, evenly across the mean, across all the x's, etc., etc. Okay? You'll be happy to know that this entire computation can be done as simple as this. You can just ask, there's a function called confint, it comes with R. You can just say, given this regression formula, just report to me all the confidence intervals, and it will give you the 95% confidence interval of all the coefficients. But I wanted to show you how it's computed parametrically. All right? It's a little bit off from mine because I'm using 1.96. They're using the accurate number 1.96 la. Okay.
Always uses 95%.
I'm just, yeah, it just uses 95%. There may be, let's see. Let's see. These questions I don't know answers to. No, there appears to be a level here. The confidence interval, you can define it as a level. I don't know what it is, how to define it yet, so I'll let you play with that, okay? There is one other thing I can do. What if I could not match the assumptions of regression? Then the standard errors are kind of meaningless, okay? But what I could do is I could just bootstrap this whole thing. And I've given you the code for it, and this is what it looks like. Essentially, what I'm doing is I'm doing a replicate 3,000 times, where I'm taking this regression formula and I'm just resampling the data, but this time, notice I'm resampling the rows of the data. I'm taking all the cars and resampling the rows. So I'm just using some number of the rows. Some will be duplicated, some will be missing. I'm resampling the rows of data. So you can see I'm just taking a sample from 1 to however many rows there are, and that gives me an index, and I'm looking at just that resampled rows in my data sets. And then I'm running my regression. I'm going to draw in my bootstrap function, I'm going to actually draw the regression line for this subsample in a very light gray color, in a transparent gray color. And then I'm going to return the coefficient for this bootstrapped estimate. If I resample 3,000 times, I'm going to get 3,000 regression lines drawn on the screen. It takes a little bit of time, so bear with me. There it is. Let me draw the original data points and the original regression line. Okay? And that's this figure right up here. What you are seeing is the black line is the original regression line from the original data set. The light gray lines are 3,000 other regression lines from resampling from this data set. What you're actually seeing is my 100%, more or less, confidence interval of regression. It's all the other slopes that I could have for this regression line. And you notice what it looks like? It's not just like, they're not just like up and down. They're all slightly different slopes going through the mean, and the mean doesn't change very much. As a result, this confidence interval has this like funnel shape. It kind of like starts off wide at the ends, becomes thin in the middle, becomes wide at the other end again. Right? They all have slightly different slopes, but they're pivoting around the mean. These 3,000 slopes have slightly different. And then what I can do is, since my bootstrap function returns to me the coefficient every single time, I can just take the 95%, I can use the quantile function to ask where's the middle 95% of my slopes. And that is another way of getting the 95% confidence interval. And I'm doing this through a bootstrap procedure. But you notice that answer is remarkably similar to the parametric answer here, right? It's remarkably similar. If my data did not meet the requirements of regression due to nonlinearity, whatever issues I have, forget multicollinearity for a while, but especially due to nonlinearity, one other thing I could do, other than trying to transform my data and do everything, is I could actually just bootstrap the data and report to you that the regression line, it's not a simple line. It's within this 95% confidence interval. Okay. So you can still get standard errors and things even when your data doesn't perfectly match all the assumptions of regression. Right? Okay, I just want to leave you with that. All the code is here. Essentially, we're just running the regression again and again on bootstrap data and getting 3,000 slopes, plotting them and looking at the 95% confidence interval. Just to give you an idea again of what the parametric solution is also doing. Okay, it's just doing it parametrically, assuming all the assumptions of regression are met. Okay, all right. This is all. This is what I want to say about applied regression, about the pitfalls of regression, about the problems of regression. There are possibly other problems, but this is like a quick introduction to the major ones. And it resolves a lot of the issues we had here with nonlinearity, multicollinearity, etc. Okay. We'll come back. Let's do it for the homework. We'll come back and re-examine the CARS data set, having solved many of these big problems. All right. Okay. Thank you all very much and have a great week.